My name is Richard. I work at Samsung Ads Canada. It's sort of a rebranding in progress. We are formerly AdGear. And if you want to follow along on your devices, this is the URL of the presentation I'm about to give you. Yeah, so I'll let you guys take photos and fetch that. Either way, so this is introducing Wrek, a library for executing dependency graphs. All right. So this is the general roadmap. I'm going to talk a little bit about the computer science behind parallelism and introduce dependency graphs as well as topological ordering, or sort of refamiliarize everyone with these, and then kind of go into the design of Wrek, splitting it into the general and the specific portions, and then sort of explain the use case we have for this at work and how Erlang/OTP really saved our bacon. So, third time now, Wrek is a library for executing dependency graphs. What does that really mean? So this is an example of a dependency graph and sort of the order in which you execute it. First, let's say you'll pull your rows from your database, and then step 2, you'll transform your data in some way, and then each of those vertices can be run concurrently, and Wrek basically makes sure that you can run this in a proper order. And being able to execute dependency graphs in a proper order is just a very, very common way of solving problems. You see this in compilers, you see this in build systems, and now you see it in Erlang. You wanted to take a photo? All right. So two of the main sort of paradigms that we think of when we talk about parallel computing and parallelism, we have data parallelism, which is sort of you have a large set of input data and you kind of split it across processors, and then each of those will work on a portion of that larger input, but it's doing the same, each processor is doing the same thing. And then you have task parallelism, a little bit more general. You can have arbitrary tasks running on arbitrary processors. Meshes really nicely with the Erlang model of concurrency. And these are used together usually. They're not mutually exclusive in any way. For example, if you have like a image processing pipeline, the pipeline itself is an example of task parallelism, but then each of the steps along the pipeline is an example of data parallelism. And so, they're very complementary. And dependency graphs fall pretty squarely into the domain of task parallelism. So a dependency graph is a directed acyclic graph whose edges model a dependency relation between vertices. So let's break this down a bit. An edge in your graph from A to B means that A depends on B. It works. I typically like to think of the edges as being flipped around, where you have the transpose of your graph, and you can say that B is a dependency of A. Because I usually think of like, oh, I'm about to do this thing, what things need to happen first. So I'm really thinking about the transpose of a dependency graph. And so the real important, the kicker here is that vertices with no paths to one another can execute concurrently. That's a typo, I'll fix that. Vertices with no paths to one another can execute concurrently. So if you have a graph like this one, we see that D equals 4 and C equals 3 don't have an edge to one another. They can be done in any order. However, you cannot mess with the order from this path from D equals 4 to B equals to A equals. You have to evaluate those in a specific order, but you can usually sort of rearrange things. And just for good measure, here's the transpose, and it sort of follows the flow of execution. And you can start at either end, and you kind of wind up at one final place. So these dependency graphs are really, really useful in build systems, compilers, all over the place in the computing realm. But one of the revelations I kind of experienced and sort of want to yell about from the top of a mountain is that we humans are using dependency graphs without necessarily really knowing it. And we can start applying all of these solutions of dependency graphs to our everyday lives. For example, to-do lists, cooking recipes, and checklists are usually secretly topological orderings of dependency graphs. So if we have step 1, you have to foo the bar, and then step 2, you need to baz the food bar, you have a dependency graph. But if you're dealing with it in list form, there are some issues. So I'm going to try and encourage everyone to blow up your lists into graphs, and then you can start dealing with your daily life in a concurrent kind of way. So here is a recipe for making pasta as a dependency graph. And when I was learning or studying some recipe in the kitchen, I was going through the list of instructions without really looking ahead. I guess I was parsing with 1 token worth of look ahead. And as a result, it took me 2 hours to make pasta. But when I blow it up into a graph, I realize that I can start doing all of these different things concurrently, because it's really just a dependency graph. So I've said topological ordering a lot of times. Topological ordering in a directed graph imposes a partial ordering. It states that for every edge from U to V, U comes before V. And so one dependency graph may have several different valid topological orderings. But what's important to know is that a topological ordering of a dependency graph is a valid order of execution. So if you have just one processor and you're doing all of these steps, you can rearrange things. However, because of the structure of the dependency graph, I can't necessarily add pasta to water that hasn't been boiled. I can't mix those two, but I can definitely move, chop vegetables, puree tomatoes, add spices. I can pepper them in whenever I want. So topologically sorting dependency graphs discards information about possible concurrency. And as someone who loves to optimize things, this makes me a little bit upset. And now I want to write out all of my recipes as dependency graphs as a result. So the thought was, what if we can just write arbitrary callbacks as dependency and structure them as dependency graphs, and then send it to something that would execute them concurrently. And that was sort of the birth of Wrek. So OTP behaviors are really useful because they let me, the library developer, impose burdens on you, the library users. I do the general part, and you guys do the specific part, and everyone is happy. And so the general part of this library is just executing dependency graphs in a proper order. And then what I leave to you is structuring your dependency graphs, as well as specifying what unit of work is performed by each individual vertex. You define a callback function, and then my library just runs it for you when it's possible. So here's a sort of little supervision tree. You wrote your module and your other module, and everything else is just there. And at the same time, I'm making pasta, and that's just the general supervision tree. So I define a callback for the behavior/module called Wrek vert. It's not a great name. Vert is for vertex. And the callback is just run. It takes only 2 arguments, the first of which is a list, which are actually your arguments. And then the second argument is a process identifier for the parent process that spawns the process that runs your callback. And I feel weird about doing that, but it's better than setting the process dictionary or passing you a record. Instead, you can just do a call to the parent process, and you can start doing things like fetching data from other vertices in the graph, and you won't necessarily get mixed up. And you are expected to return a pair OK and some term, or error and some other term. And when you want to put everything together in a graph, you have something resembling an adjacency list representation, where you have either a map where the keys are arbitrary terms which name your vertices, and then the values are maps with these 3 keys defined, which is the module, the name of your callback, the arguments that you want to pass into it, and then the dependencies, the proper names of all of the other vertices that it may depend on. So this is just your standard fare adjacency list representation of a graph. And when you start your graph, the map is read into a digraph, which is a really fun module for running graph algorithms as part of the Erlang standard library. A digraph graph is really 3 ETS tables. It's really fast and super fun. And basically, every vertex that has no queued or running dependencies is just started. It hits the ground running. And values that get returned are stored as labels inside of the graph, and you can then fetch them later, which is why you need the process ID. You have to pass that into this function in order to get results back. And if you supply a event manager process created by genEvent, and you pass that in to Wrek, it will start to pummel your event manager with these event notifications with timestamps and everything, so you can suddenly start adding handlers for things that happen as your DAG is executing. And if your callback returns an error or throws some exception, it will just crash the entire graph. So if you really, really want things to succeed, I unfortunately give you the burden of catching errors. So this emerged from a need of alleviating some CPU pressure from our bidding servers, which are just running at full CPU all the time. And unfortunately, they're all wasting a CPU core doing the same kind of calculation that kind of just gradually got more and more expensive over time. And so it finally was decided that we needed to kind of pull that calculation off to a single server and then ship the result out to the edge. And in the interests of shipping really quickly, the first version was implemented with cron jobs and bash scripts, because that always works. And it kind of worked. One continual pain point that we had was that logging wasn't super great, but we started to see this pattern emerging in a couple of other services as well, and we decided that we wanted to create something a bit more robust to do this. Just have a group of servers that do calculations for the sake of generating state for these other services. So this is where Erlang comes in handy. In the interests of iterating quickly, it made sense to have a library that could do 2 things. The first was running callbacks. That's pretty straightforward. But the other thing that we wanted to do is we wanted to just take in our existing shell scripts and have this framework run them without really any changes. And shell scripts are really secretly topological orderings of dependency graphs. And so this is why Wrek exists. And using the Erlang library, we are able to easily slurp in our existing scripts, and we can do what we want with standard error and standard out. And now we are in a position to sort of replace, in a piecemeal kind of fashion, these large, brittle shell scripts with dependency graphs made up of smaller shell scripts or Erlang callback modules. And as we started replacing these, we started seeing more concurrency emerging, and as well as more information coming in for the purposes of logging and monitoring. And so thanks to Erlang and OTP, we're very flexible with how we handle events generated by Wrek with adding handlers. And one of the cool things that we want to, or 2 cool things that we want to start doing is exposing the status of graphs as they're running through some HTTP endpoint. You open a page, you see your graph, things turn green. It's really satisfying. And another thing that we are interested in looking at is establishing contracts between servers and exposing information to each of the servers so that they can check if there's agreement and raise an alarm if there isn't. So dependency graphs are useful for exposing opportunities for concurrency. They show up all over the place, not only in computing. They're all around us in everyday life. Wrek is an application that executes dependency graphs only in computing, not in your everyday life, unless you like it that way. And Erlang OTP has been really, really helpful in letting us ship quickly and start paying down our technical debt imposed by our shell scripts. And I'm deeply grateful for the digraph module in the Erlang standard library, as well as Erlang by Sergey Alenikov. They really do the heavy lifting in Wrek. And so in conclusion, if you enjoy thinking about decomposing these larger tasks into dependency graphs of smaller tasks, Or if you don't know that that's a thing, you should try it. It's fun. Get some paper and doodle. Or if you want to incrementally replace a mess of shell scripts with smaller, more concurrent ones, or just Erlang callbacks, then take a look at Wrek. Here is the repo, and here is the link to the digraph documentation, as well as to the repo for Erlang, which is really fancy for starting external processes. And thank you very much.
Questions?
Would this be a suitable tool for running like large-scale, like machine learning algorithms?
Interesting question. I don't know. I wrote it mainly to run shell scripts. That said, I'm really excited to see what kind of pain is experienced if you want to, construct large neural networks or other training scenarios.
Okay, this would be fun.
Yeah, it definitely would be fun.
Hi, I was just wondering if you have a demo or any code examples you could show us?
I do, not here, but as part of hyping up the conference, I did write a blog post. It's part of the CodeBeam blog. They published it, I think, about 2 weeks ago. I go and implement the little pasta dependency graph, and so I now have a program that looks like it's making pasta. If you want to check it out.
Did you implement any way of sort of saying that I only want to do, or do you only start everything that's possible concurrently? Or is there a way of saying, hey, at the most, and the number of things? And also, is there a way of sort of saying, hey, I want to do part of my graph, but these nodes are part of the graph?
So I haven't really accounted very much for running these dependency graphs in a distributed fashion. And as far as running only subsets of a graph, that's something I'm trying to figure out how to do it right. I'm kind of approaching the problem from another aspect of how do you attach more to a running graph. It's tricky. I'm not sure how I'm going to do it yet. But right now, the only option is you have some way of pre-processing, sort of examining the state, and then you use that to construct your regular Erlang terms that you can then convert into a dependency graph. So really, your only option is pre-processing right now. Thank you.